Okay,
Okay.
maybe, yeah, we can start. So, yeah, ladies and gentlemen, good evening in China and good afternoon in Europe. So welcome you to participate in the open seminar in Frontier of Nuclear Physics. I am Yigama from Fudan University. Today, I'm happy to chair the 33rd seminar of this series. The present seminar will be given by Professor Adriana Pálwiąy from University of Würzburg, Germany. She is one of very active scientists in the field of the light matter interaction community. So this seminar series is hosted by the key laboratory of the nuclear physics and ion beam application Institute of the Modern Physics and the Department of Nuclear Science and Technology, as well as Shanghai Research Center for Theoretical Nuclear Physics, National Science Foundation of China. The seminar is also co-organized by the Journal of the Nuclear Science and Techniques, as well as its Chinese edition, Nuclear Technique. The seminar is open to the scientific community, particularly for the nuclear physics community. And this seminar is also shared by the coshare.com. Professor Pálwiąy will give a talk on coherent light interaction with nuclear from ultraviolet to the gamma rays. And let me briefly introduce Professor Adriana Pálwiąy. Professor Pálwiąy is a theoretical physics professor at the University of Würzburg in Germany. By understanding light matter interaction at the borderline between atomic, nuclear, and quantum physics, she aims at obtaining quantum control over the nuclear transitions. Adriana studies physics in Bucharest, Romania, and received her PhD in theoretical physics at the Justus Liebig University in the Gießen, Germany in 2006. She later moved to the Max Planck Institute for Nuclear Physics and became a global leader in 2011. In 2019, she was awarded the Hertha Spanner Prize of the Germany Physics Society and the Ludwig Prize of the University of the Gießen for her work on X-ray quantum optics. Since 2020, she is the Heisenberg Fellow of the Germany Research Foundation, first at the Friedrich Alexander University of the Erlangen, Nuremberg, Germany, and since April 2022 in Würzburg. And Professor Pálwiąy is very famous in the field of the X-ray quantum optics. Also, now she did a lot of excellent work, like for the nuclear isomer, and she has already published a lot of great publication, including Nature Photonics, Nature Physics. If I remember correctly, and she has already published close to the 20 physical review letter papers on some frontier physics topics. So we are very happy to have her give a talk on this topic. So welcome, Professor Pálwiąy.
Thank you so much for thank you for this kind and long introduction. So it is my pleasure to give a talk today online, and I also appreciate that you're all here, although for you it's pretty late in the evening already. Yes, so my talk covers now quite a broad range, generally speaking, about coherent light interacting with nuclei. But there will be 3 examples, and they really go from ultraviolet to X-rays and to gamma rays. Now, I hope you hear me well, at least. If the slides are not perfect, if not, you should tell me. Yeah. Otherwise, I will start with a historical perspective, namely reminding ourselves that now 62 years ago, that Myman was inventing and producing the first successful laser. And laser, if you want, is something which is very strong light created from atomic transitions. It's typically in the optical or infrared. And we use that very strong light, basically coming from atoms or molecules, to control, again, other atoms and molecules. So if you want, it's kind of mutual control of laser light and atoms. And this has really brought a revolution, not only in atomic physics, but later on in all kinds of technologies of metrology. So right now, there's so many fields which are very much influenced by lasers. And it's, you know, a little bit of control we always had, right? Already since the 19th century, when Bunsen and Kirchhoff in Heidelberg were, you know, burning some atoms, heating them up, and basically with incoherent excitation, observing afterwards passively the decay. This actually has now evolved so much that we can really have full control of single atoms and ions. So laser was really very important for this control aspect. And here I show you a picture from the ion traps of Dave Wineland. Now this is the control we have right now. It's really on the level of single atom, single ion, single photon. And this gives us possibilities for full control of quantum dynamics using lasers, and typically either traps or cavities. One picture comes from Dave Wineland, and the other picture comes from the Serge Haroche group. They both shared the Nobel Prize, 1912. And this is something that has been enabled by lasers. Now, if we look at the electromagnetic spectrum, typically lasers are rather here and visible or infrared light. And what I will talk about today is going more in this picture to the left. So towards higher frequencies, towards shorter wavelengths, namely here. And then actually in this range, we no longer have transitions in atoms which are in neutral atoms, which are of interest, but we can rather think of addressing with X-rays or with gamma rays atomic nuclei. So in principle, also nuclei have energy levels, and these energy levels can be used, right? So this laser light or coherent light with higher frequencies could drive nuclear transitions. And this could also bring with it kind of a new revolution with new applications, several of them. I will mention now, so as an incentive, if we go now towards high frequencies, starting actually from VUV, vacuum ultraviolet, which is here not very far from visible, going, however, really up to X-rays and gamma rays. And the incentives that I would like to mention, or I will touch in my talk, are very much also related to the fact that we now do have a number of novel coherent light sources. For instance, in the X-ray regime, we have the new X-ray free electron lasers. You have here a picture from the airplane taken over LCLS in Stanford, which is the first X-ray free electron laser, which became operational 2009. Sakla in Japan started 2011, and there is Petra 3 in Hamburg in Germany, who also has light since 2016. And if we are interested in coherent gamma rays, we might like to go to the extreme light infrastructure, nuclear physics pillar of it in Bucharest, Romania. It's the place where I was born, which is still under construction right now, but which promises to deliver intense and also coherent gamma rays. So we have these new sources, and we have a couple of interesting ideas. What can we do to have such coherent light interacting with nuclei, atomic nuclei? And the first incentive that I'll bring on the table is actually, it does not require X-rays and does not require gamma rays. It just requires something like 8 electron volt. This is a special nuclear case in which a nuclear transition is only 8 electron volt. Now, you probably all know that we define the second and we measure time with atomic clocks.
Recording stopped. Recording in progress.
Okay. So since 1967, the second is defined with a hyperfine transition of a cesium atom, isotope 133, and it's a hyperfine transition in of the 6s electron. And there's thorium 229 isotope, which has this very, very low-lying first excited state in the nucleus, above the ground state. This actually poses for us the chance to build not an atomic clock, but really a nuclear clock. For this transition, actually, the ratio between width of the excited level and the energy of the transition is about 10 to negative 20, which is great. And on top of that, actually, what we do like about nuclei is that they are even better isolated from the environment than atoms, right? Because they do have the electrons around. So this could be a better frequency standard. And not only that, but we could ask it also some questions that maybe we should not ask, for instance, where the fundamental constants are constant over time. This we can do also with atomic clocks, right? We can ask whether, for instance, the fine structure constant alpha, which determines the electromagnetic force, is constant, but actually here we have the nucleus, so we could even look for constants which are related to the strong force. So that's kind of interesting. But for this, again, we would just need vacuum ultraviolet light. If we go towards X-rays, well, X-rays are special because they are very good for penetration, and this is actually the way they were discovered. I am lucky now to work in the university where Wolfgang Röntgen was discovering X-rays about 120 years ago. And he was the one who discovered that they penetrate very well through material, also through human tissue, for instance. X-rays can be very well focused. And because they do not suffer very much of the diffraction limit, right? Since the wavelength is very small. So in principle, one can address with X-rays, instead of a full atom matrix, you can really focus in principle up to the size of an atom. And this is why they are very cool, because they could give us ultimate miniaturization. They can, you can have sensing with very good spatial resolution because of their precision, and also energy resolution. So the question here is the other way around. If X-rays are so cool, can we control single X-ray photons using nuclear transitions? Because you could use the resonant interaction basically between X-rays and nuclei, and nuclear transitions. So this is also an interesting point. And the other point that I will mention is if you're going really for coherent gamma rays and would like to see how the laser nucleus interaction works there, as the plans are for the extreme light infrastructure, it turns out that if you're plotting, for instance, the energy as a function of angular momentum, there's always in nuclei, there is the so-called Erast line. And this is basically the line. So the energy for a state according to its angular momentum. So if you have very high angular momentum, you cannot have very small energy, right? It's going up. And so far, if you want to produce very high excitations in nuclei, and I'm talking now about hundreds of MeVs, one uses heavy ion collisions, and these heavy ion collisions bring not only energy, but also high angular momentum. Whereas if one would be able to have coherent MeV photons, then one could have photo excitation, maybe with multiple photon absorption, which would bring us far up here, where we are far away from this Erast line. And this is actually a regime which has not been investigated so far. So here we could basically maybe also learn more about nuclei themselves by tackling them with coherent MEV photons, not X-ray photons. So this will be, so to say, the incentives that I can present on what we can do, and they also then align to my outline. So I will start from small frequency to high frequency. We'll first discuss about nuclei, this specific nucleus, thorium-229, interacting with BUV photons. Then we will discuss about taming X-rays, so controlling X-rays with nuclei in specific structures, these thin film cavities, which allow us to implement a number of very nice and interesting X-ray quantum optics schemes. And in the last part, I will tell you a few words about our work on laser nucleus interaction with coherent gamma rays. So, what's so special about thorium? Well, thorium was discovered about 200 years ago in a mineral in Norway. And this is why it was given this name thorium, because Thor is a Norwegian or Scandinavian god of thunder. It has 90 protons and the rest 139 neutrons. And this turns out to have the lowest excitation energy of all approximately 180,000 presently known excited nuclear states. What we know about its energy is that it's 8.2, more or less, with some error bar. And we believe that the radiative rate of this transition, or divided by the energy, would be of something like 10 to the negative 20. You see here in the plot, which is taken from this Nature paper, Pálorszáy von der Wense, energy of some transitions as a function of half-lives. And you see that most of them are up there at kilo electron volts, tens of kilo electron volts, or MeVs. Down here is thorium. It's one of the exceptions. The other exception is uranium-235, which has a transition at 76 electron volts. And this orange cloud over here is the region where we have the optical clock transitions. And now we would have a nucleus which has a kind of VOV clock transition, which is very nice. Now, thorium is kind of an anomaly for nuclear physics. And I just, with one slide, want to tell you what we have found out coming from nuclear structure and trying to understand how can it be that one has this almost degenerate first excited state, almost degenerate to the ground state. So the model that we have developed, or more or less, let's put it this way, Nikolai Minkov has, it's his model and we've been working together, but he's the expert. It's a macroscopic model, takes the following picture. Let us take first out of the 229 nucleons, 90 protons plus an even number of neutrons to form an even core. This is done often in nuclear physics because you want to have the spins, right, paired. So this is why you take pairs of nucleons, because both protons and neutrons have spin 1/2. So we have an even core, and it turns out that this even core presents in the actinide region quadruple octopole deformation. So it's basically something like of a shape of a pear, what you see here. So this blobs that you see below, these are the ones which show this even core with its quadruple octopole deformation. Now, there's one neutron, however, which is unpaired because we have 229. So there's one additional neutron on top. And this one additional neutron on top moves around, so basically rotates around the core. And one has basically also in the description of this movement, the Coriolis interaction between the core and this single particle. So one has basically, so to say, collective features of the nucleus in the even core. We put them all together. We see them as a collective form. We have the single particle features from the single neutron, and we have the Coriolis interaction between them. And this type of model appears to describe pretty well everything that we know about thorium, basically the low-lying levels up to 300 keV, the magnetic moments, the root mean square radius, and everything that we know from experiment at the moment. And in this case, it does appear that there is the first excited state very close to the nuclear, to the nuclear ground state. Nevertheless, the model itself in nuclear physics, one would never have precision of 8 electron volts. So we are happy that, for instance, in our first calculation, we got 0.4 keV, right? Not 8 electron volt, but 400. It was still very nice. It appears, and that's kind of really interesting, we have this, so to say now in a newer work, that in the actinide region, there could be more such phenomena. So also other nuclei could have kind of degeneracies, but 8 electron volt for nuclear physics still remains a miracle. So the probability that some other nucleus, a part of thorium-229, would have exactly something so low that it can be addressable by a UV laser is still very low. And to a certain extent, there is already a confirmation of my statement, because there is uranium-235 with the 76 electron volt transition. It is for nuclear physics almost degenerate for the ground state, but for practical purposes of a clock, it's not possible to, not so easy. It's not possible, but it's not so easy to drive with a narrow band laser, what you would need for a clock. Okay, let me come back to more stories about thorium, which, since they are not with light, I will just pass through so that you heard of them, but I will not go so much into detail. Because the nuclear transition has such a low energy, there's a lot of communication with the electronic shell. Now, you're all aware that, for instance, an excited nucleus can not only decay via emitting a photon, but in certain cases, it can also decay via internal conversion. And the internal conversion is that the excited nucleus transfers its energy to an electron in the atomic shell. That electron is leaving, it's kicked out. So afterwards, you have an ion, so the atom is ionized. So the energy of the nucleus is transferred to the electron goes out. And in case of thorium with 8 electron volt, this is sufficient just to kick out the outermost electron in a neutral thorium. The outermost electron is a 7s electron. Now, radioactive decay, actually, so far, I could have said it was never observed, but now recently there was a preprint on the archive saying they did observe it. So this is why the question mark here. So maybe the radiative decay has just been observed, but internal conversion was the first channel to be observed for thorium. And this was the first direct evidence of the isomer back in 2016, so 6 years ago. Now, of course, one of the main questions we have is we would like to know exactly with precision what is the energy of the isomer. And so far, you can imagine it's very difficult to have good precision on this very small value. So in principle, if you are able to measure the energy, kinetic energy of this electron leaving here, this kinetic energy, plus the ionization potential should be giving you the nuclear transition energy. And in the group of Pálorszáy in München, they have measured the spectra for internal conversion electrons. And out of the spectra, which actually looked a bit different than we would have expected, we were able to extract the energy out of the measurement. Now, why? So this basically is the kinetic energy of the incoming electron, and you'd expect that there is some clear cut. There is no clear cut because it turns out that actually here in the process, the 7s, the outermost electron, can also be excited to some further still bound but excited electronic states. So this is why one has here not a very clear drop, but some smooth drop. So this is why actually our calculations of internal conversion rates in my group were very important to extract the energy out of the spectrum. And this is actually how we made it for the first time for me in my life on the Nature cover back in 2019. Now, it turns out that not only this process is important, but also other processes could be important that couple the nuclear transition with the electronic shell. Namely, imagine now that you have the nucleus excited, but there is, for instance, no internal conversion possible because you are in an ion, and then the energy, 8 electron volt, is not sufficient to kick out the electron. But what could happen is, for instance, that a process called electronic bridge is happening. This electronic bridge basically considers now the case in which internal conversion is not possible, and there's also no corresponding level exactly in the electronic picture, in the electronic states. There is no level which corresponds exactly to the nuclear transition energy. But what could happen here still is that, for instance, the nucleus goes down and the electron comes to a state which does not exist. This is, of course, just a theoretical construct. This is what we call in theoretical physics a virtual state. And then this virtual state afterwards, of course, decays and can emit a photon. So we have, at the end of the day, nucleus has de-excited, there has been some atomic transition, and there's also some photon coming out. So in total, we have energy conservation, and we went via this virtual state, basically. So this would be the process of electronic bridge for nuclear decay. Unfortunately, in the literature, electronic bridge is used both for nuclear excitation and for nuclear decay. So one has to bear in mind what exactly the case is that we are talking about. For instance, if we want with nuclear excitation, what we need now is to have the atomic shell excited. This energy should be transferred to the nucleus, but you see it's not matching it exactly. So the energy of any atomic transition, electronic transition does not match the nuclear transition, but we can go again via this virtual state. So we can go via the virtual state, excite the nucleus, and then a photon is emitted for this electron to arrive at the real state. Yeah. And actually this can happen in both ways, right? So you can first have the nuclear transition happening and then the photon, or one can have first the photon bringing you to a virtual state, which is exactly where it should be, such that afterwards you can transfer energy to the nucleus. So in principle, there are two possible virtual states for this scenario to have energy conservation up to the end. So this is the electronic bridge with nuclear excitation. And I basically wanted to tell you about our two scenarios that we investigated for this electronic bridge. One of them is to take this process in highly charged ions. And the picture is here. Basically, the nucleus is in the ground state, and there is an excited electronic shell, not yet at 8 electron volt, just at 4. And then on top, you can come with a laser photon. So this is again with photons, but the photons discuss to the electrons, and the electrons discuss with the nucleus. This laser photon actually we like because, see, if we start from this excited electronic shell, the laser photon does not need to have 8 electron volt. It needs to have just 4. And this is good because we have better sources for this. Now, this will bring us up to a virtual state, which afterwards decays. And this energy is exactly the energy the nucleus would need. So electron goes down, nucleus goes up. You might ask me why, where from do we have the excited electronic shell? And the specific scenario we were thinking of was, together with Jose Crespo at the Max Planck Institute for Nuclear Physics, we were discussing a scenario on an electron beam ion trap, which is the beast over here. So it's basically a device which creates highly charged ions, because the scheme here is in thorium-35 plus. The advantage here is that you can come with a laser no matter what intensity, and there will be no further ionization because 35 plus is already, right? The electrons which are left are quite well bound. And in this electron beam ion trap, there are electrons which keep colliding to the ions and thus generating the ions. And through these collisions, there's also some excitation. So basically, there would be in steady state a 17% excitation of this state. So 17% of your ions would be already here. And then you can address with this laser photon and have this electronic bridge happening. And the advantage is here, having a better laser source, one can really scan quite well, and one can then have a sub-milli-electron volt determination of the isomer energy. So the plan and so the proposal basically published here in Physical Review Letters 2020. This is one scenario, and the other scenario would be to go for thorium doped in VOV transparent crystals. For instance, calcium fluoride is such a crystal. And one can, it's VOV transparent, so it has quite a large band gap, up to 12 electron volt. And putting thorium in, however, creates some defects. And it turns out that these defects are actually not completely away from thorium, because it turns out that there are some fluorine interstitials which come, the green ones, which come to do some charge compensation when thorium comes in, because thorium likes to grow in this calcium fluoride crystal is 4+. It replaces the calcium. Calcium is just 2+. So this requires these 2 fluorine interstitials. And these create the defect that a 2p electron from this interstitial fluorine likes to move to the 5-dopant thorium. See, they are quite close to each other. So this actually generates some electronic states in the band gap that you in principle would not like, but for us it turns out that they could be in the vicinity of the nuclear transition energy, so around 8. And this is basically depicted here. So the bottom lines are, so to say, the Fermi level, and here the C is the conduction band. So the gap is basically between the lower level and the C. And the defect state which appears could be around the isomeric energy, either a little bit above or a little bit below. Here we are not trusting theory so much, the density functional theory results to say that we are completely sure where it is, but it seems to be around 8 electron volts. So it could be a bit above or a bit below, and this then can be taken care of with an additional laser in the similar manner. So starting from the defect state below, we would do exactly as in the highly charged ion scheme. One could have an additional laser photon, which would be now optical, to pump up to a virtual state which is equivalent to the isomeric energy, and then have the bridge over here. Or even if the defect state is above, you could have some stimulated scheme with a laser to stimulate the photons that you need from the electronic bridge in order to reach the virtual state, which then helps you to transfer the energy to the isomer. So basically to the nucleus, to the thorium nucleus. And the nice thing is, it turns out that this process could, by shortening the interrogation time, would allow a clock based on such a solid state calcium fluoride to work to reach a better accuracy. So this would be relevant if we try to build a clock in the calcium fluoride setup. And finally, the very last result that I can show you is coming towards X-rays now. So a few years ago, we were looking at quantum optic schemes where you have a 3-level nucleus or atom or whatever, and you come with 2 pulses to drive a first transition and a second transition. Or more interesting, you come actually in with the pulse is the opposite. You come first with the red pulse and then with a blue pulse, and this transfers population directly from 1 to 2. This process is known in quantum optics and is called stimulated Raman adiabatic passage. And now, if we try to do this for thorium, it happens so that thorium has the ground state, the isomeric state would be this 2, and there is another level at about 30 keV, so 29.19 keV above. So we were considering and doing this stimulated Raman adiabatic passage, now not driving directly 1 to 2, which would be having a VUV laser, but really going with X-rays up and with X-rays down. And this actually also turns out to be an interesting process. Of course, you need for that strong X-ray sources. And this is kind of a good transition towards my second topic, which is how to tame X-rays. So now no longer thorium, but maybe other transitions. Namely here, one would consider Mörsbauer transitions. So transitions in nuclei, which can occur in solid state recoillessly. And the typical example is iron 57, which with a 14.4 keV Mörsbauer transition, actually pretty well known in Mörsbauer spectroscopy. And to a certain extent, this is maybe less nuclear physics in the traditional sense, because that's rather nuclear condensed matter physics. So what I would like to present to you first is a specific setup where we want to place the nuclei in order to get good excitation of these nuclei and to get some interesting effects. And this specific setup are the so-called thin film X-ray cavities. So the goal is now to have X-rays interacting with nuclei, but we don't consider single nuclei, we consider many nuclei at the same time. These nuclei can absorb and re-emit that light recoillessly, that X-rays, those X-rays. And the specific setup is that we have a sandwich of very, very thin layers. So in total, maybe all this sandwich over here has 50 nanometers thickness. And we consider a first layer, which has a high-Z material. This high-Z material will interact with X-rays coming now in so-called grazing incidence. Grazing incidence means that the angle is very, very small, so the X-rays come almost parallel to our surface. And because of this high-Z material, there is at certain angles a standing wave created inside here. Now, the standing wave is interesting for us because this will be a kind of cavity field that we can control by the incidence angle. And we want now to place our iron layer within the standing wave at a certain position. And to do so, we have some low Z material buffer, which is this yellowish level, or the two yellowish levels. They are basically used in order to be able to place the iron layer exactly where you want it to have. The plot here shows you the reflectivity of this cavity, so the detector, as a function of incidence angle, and you see these dips, these very, very narrow, good dips. These are the places where the electronic reflectivity is zero, and these are the places where basically the entire light is inside. And this is the picture of, so to say, the light intensity inside for the first minimum. The second minimum would have 2 blobs, and the third minimum would have 3 blobs, yeah, in the middle. So this is basically the standing wave formed inside the cavity. And with the standing wave, our nuclei will interact. And the nice thing about all these nuclei is that they have some way of behaving collectively, since they all interact recoillessly, right? A photon, which is resonant, can be absorbed and re-emitted, and absorbed and re-emitted many times. And there is a delocalized excitation, so to say, over the whole sample. And this allows us to have collective effects. Now, just one picture to show you the cavity. I told you it's very thin. So basically, you know, this polished surface that you see here is actually the entire cavity. All the rest, I mean, the thick 1 millimeter thing is actually the substrate, which is a silicon wafer. But the polished surface is the other 50 nanometers that we have over here. So high Z material, low Z material, our iron or Würzburg isotope, and again, low Z material and high Z material. And you'll see later, actually, we can have also many such levels. So this is kind of the prototype with a single iron layer, but we could have also more. Okay, interesting about these cavities is, as I just tried to stress, that the nuclei behave collectively. Let me show you a very interesting result from 2010, an experimental result that really demonstrated that this cavity has so-called superradiant decay. So the nuclei in it decay faster than a single nucleus. So what was measured is here the detector, the scattered photons as a function of time, because this was an experiment performed at a synchrotron. So there is the synchrotron pulse coming. This sets t equal to 0, right? So the time. And then later on, you measure the response. There's plenty of electronic response, which comes very quickly, and this is time gated. So this happens basically here almost at t equals 0. After 1 nanosecond, what you get is basically what comes from the nuclei, because the iron nucleus has a lifetime of 141 nanoseconds. So this nanosecond response are the photons which have been interacting with the nuclei already. And now on this log plot, up here is what we would expect from this 141 nanosecond lifetime that we know from the nuclear tables. So this would be the spontaneous decay rate of a single nucleus, the incoherent if you want spontaneous decay. The decay that has been observed for these cavities are these two lines. They are two because they are for two different cavities. And with one of them, we see an enhancement of factor 42 in the exponential, because this is a log scale. And with the other one, an enhancement of factor 60. So as it turns out, this cavity field, the standing wave which forms inside the cavity, excites a radiative eigenmode. And then we get this coherent enhancement speed up of the decay, so superradiant decay, which means that basically we have something much faster. the nice thing about it is not only that it's fast, because you tell me, then take a different nucleus which decays from the very beginning faster. What's the point? Well, the point is that this superradiant decay can be controlled. It turns out, for instance, that you can switch it on and off. For instance, I'll show you here some older results from my group, where we could show that by magnetic field switching in the sample, so basically by turning on and off magnetic fields or rotating magnetic fields, one can switch off and again on the coherent superradiant decay. And since you've seen here that this is actually much faster than everything else, it means that you have an additional decay channel for a system and you can control it. So this gives us control over the X-ray photons. And the result here is actually one of our older works with Zhangjin Kong, where the idea was that in such a cavity, if you have at the beginning an external magnetic field, which produces hyperfine splitting of your ion transition, and then while the pulse is propagating through the sample, you're switching the magnetic field off, then it turns out that if you're plotting here the electric field of the pulse, during the time that the magnetic field was switched off, actually also the field disappeared. So the X-ray photons have been basically stopped inside the cavity because the pulse has been mapped to the nuclear coherences. And once the magnetic field of the nuclei is switched on again, then the light will be released again. So this was actually a very nice result by Zhangjin to see how one can store single X-ray photons in such cavities. Now, another interesting result, also together with Zhangjin, was to kind of mimic the stroke coupling regime with X-rays, which we basically interpret as X-ray ping pong. So if we imagine people playing ping pong, right, you have a ball exchange several times, and you'd like to do this many times before you lose the ball, right? So this is the essence also of strong coupling, that the system is interacting with the photon field many times back and forth, exchanging a photon before that photon is lost out of the cavity, typically, right, in cavity QED. So let me put now this interesting picture from sports into our cavity discussion. So what we were taking at the time was a nanostructure, which is more complicated. It does not have just one iron layer, it has two iron layers. And these two iron layers are the green ones here. As before, we have this evanescent coupling. So the pulse comes in at a very, very small angle, almost parallel to the surface. We measure the detected reflectivity. And in principle, if we do this experiment, and the experiment was done with synchrotron radiation, then per pulse, there is just one single photon, which is really resonant to the nuclear transition because the nuclear transition is very narrow. So each pulse actually brings one single photon. And then this single photon can excite either a nucleus in the first layer or a nucleus in the second layer, right? And where exactly it's not clear because it's, within the layer it's delocalized, and also which of the layers is not clear. And there are also decay rates because from each layer that photon can be lost. So basically what we're talking about is the ping pong ball is the resonant X-ray photon. The rackets that we use are actually the two layers. It's either excitation in first layer or excitation in second layer. And we do have, via the cavity field, we have a coupling between the two layers. So basically, to be able to play this game for a long time, you would need that the coupling between the two layers is actually stronger than the decay rates, right? Because the decay rates are the loss. This would be I've lost the ball. And you'd like basically to be able to exchange many times the excitation between the two layers. So put into a level scheme of quantum optics, you have a ground state where there is no photon, and you have excitation in layer 1, excitation layer 2. You have the coupling via the cavity field, so the interlayer coupling, and you have the two decay rates which lose the photons, so you come to the ground state. And the idea would be to have this stronger than decay rates. And it turns out that in these cavities, everything is actually, all these quantities are controlled by the incidence angle. So if we plot here the rates as a function of the incident angle, we see that the blue one is the interlayer coupling, so the colors are the same. Red and green are the decays, and the blue one is the omega, the interlayer coupling. And we see that there is an incidence angle range for which we have a much stronger coupling rate than the decay. And this is what we call, so to say, mimicking the strong coupling regime. Here, it's not really the atom interacting with the field, but it's these two excitations, if you want, these two polaritons interacting with each other. And they interact with each other here much stronger than they can lose the photon. Luckily, there was an experimental team in Hamburg who also was able to confirm our predictions. So we have here in energy, so to say, the splitting which occurs because of this exchange back and forth all the time. At the detector, in energy, you'll notice a splitting. Although you should have a single line, you see a splitting of the line because of this exchange. So it's basically the equivalent of the vacuum splitting from cavity QED. And if you look in time, the time domain, you see Rabi oscillations in this because of this splitting, which have to do, so basically at the detector, you see, because of the oscillation of the excitation between the first and the second layer, you see also an oscillation of the detector. So this is something that could be observed, and we are very lucky to get on the cover of Nature Photonics, and we had then the experimental first author and the theory first author, Shanjin, for this very nice, basically, publicity for quantum optics with X-rays, because we made it on the cover with quantum optics with X-rays. And actually now, since then, we have continued first in developing better theory tools to understand these multi-layered systems, because we want to go now to very many multi-layers and to design more and more complicated schemes. So this is where Shanjin was working and developing a green function formalism, which treats a fully quantized electromagnetic field and can be used for any multi-layer structure. So it's a very powerful tool. And now with this, I mean, for instance, this example here is for the reflectivity as a function of detuning an angle for 30-layer cavity, right? So a cavity with 30 iron layers. And this is something which is, so you need to have the proper tools to treat this. And now, actually, before we go to 30, I just wanted to mention briefly that we have now a very interesting project where we are treating 3 iron layers. And here the trick is that we can implement some concepts from quantum optics. Namely, one can place 2 layers in a place where the field is strong, and the 3rd layer in a place where the cavity field is 0, almost 0. And then it turns out that one develops, so to say, a combination of a dark state, a bright state, and only the dark state interacts with the red layer, which is in the middle and basically sees no cavity field. So this is actually a tool which has been used in the optical regime to generate effective photon-photon interactions and non-classical states of light. And now we're trying to do this with X-rays. And we're also very lucky that Shanjin was able to organize an experiment at Spring 8 in Japan at the synchrotron, and there is data on that, and we hope to be able to submit also the manuscript soon. It's a very, very interesting result. So you'll hear from us soon, I hope. Okay, with this, I finally, after already quite some time, come to my 3rd topic. So I'll jump now for the last 10 minutes into a completely different topic, which is maybe a bit more about understanding nuclear dynamics at high excitation energies. So now we leave VUV and we leave X-rays and we really go to gamma rays. And the entire project here has been fueled by the idea that one could have at the extreme light infrastructure also photons which could be coherent. So MEV photons which would have very good temporal coherence. And their idea is basically to use a Compton backscattering and have basically an electron, a flying electron mirror on which an optical laser is backscattered. And if this mirror has a high degree of perfection, then basically the backscattered light would also maintain its coherence. So coming with a coherent optical laser and having a very good electronic mirror, one will also have coherent MEV photons. Now, I have to say from the very beginning, this is just a plan and it's not done yet. And Eli should also first come online, but never mind. Okay, so what would we do if you would have such a thing? So if we really have laser light coherence for MeV photon energies, then in principle, we could have multi-photon absorption, so absorb several photons on the same pulse. And these pulses are actually very short. They are like femtosecond pulses. So we could really investigate then the transition from a system of strongly correlated particles, meaning the nucleons inside the nucleus, to independent ones. And as you'll see, one can hope to produce nuclei far from nearest and also far from stability. Now, this is again hypothetical because the source does not exist yet, but we were asking ourselves simply the question from theory side. And I think if we are thinking now of this, collection of nucleons, which is the nucleus, and we have somewhere a Fermi level, we typically like to put them, to put these nucleons paired, as we discussed, because of the spin. And imagine we are having an even A, and this is our Fermi level. At the end of the day, we can also consider this as a Fermi gas. And then we are discussing about level densities and not about exact levels. And in nuclear physics, it's often so that if you have some excitation here, then right below the Fermi level, there is a hole, and above the Fermi level, there's a particle. So we start describing such excitation in the picture of particle hole pairs. And then the theoretical description works like this, that you have in the nucleus the mean field, then you have additionally some nucleon-nucleon collisions, which we call residual interaction because it's the residual to the mean field, right? So what's left out. And we have statistical coupling of all possible states with the same energy. Again, we are typically very statistical at this time. At this moment, we're discussing about level densities, and we're discussing about the fact that you obtain basically equilibration pretty quickly. And this equilibration is very fast. So this is why in nuclear physics, there are such things like a so-called spreading width. So it's often on the level of 5 mega electron volt, which means that within femtoseconds, so 10 to negative 21 seconds, equilibration has been reached. So basically, if you have, for instance, an MeV photon coming in and generating a particle-hole pair, then this residual interaction will quickly try to redistribute the energy that has been brought in. So basically the energy between these, between the particle and the hole here. So this additional energy which was brought in by the field to many other particle-hole pairs. So instead of having one particle, one hole, one would have 2 particle, 2 holes, or 3 particle, 3 holes. And this happens again very quickly on the level of 10 to negative 21 seconds. So if we're thinking now that we have this photoexcitation, so photons are absorbed and photons are on the level of MeV photons, we have the photoexcitation, which creates particle-hole pairs, but we also have the residual interaction, which distributes the original energy of the first particle-hole pair on many, many, many particle-hole pairs. And actually the question is now, what's faster, right? So if a photon comes very seldom, right? So every 1 minute the photon comes in, then of course there is plenty of time for the residual interaction to distribute, right, the energy over many particle-hole pairs. And this would be the perturbative regime. Together with Hans Weidemüller in Heidelberg, we were investigating the other two, the quasi-adiabatic and the sudden regime. So interesting it gets if you have a source which is strong enough to deliver photons or deliver coherent photons, which by their being identical enhance or boost the excitation to reach the so-called quasi-adiabatic regime, where this photoexcitation is similarly quick or similarly strong to the residual interaction. And for this one, we really need that the effective dipole width, so to say, or dipole excitation, reaches also the MeV level as the spreading width. And if we would have an incredible source, which would have plenty of photons and all of them coherent, we could maybe reach even the sudden regime where the photoexcitation brings in photons quicker than the nucleus can equilibrate and the residual interaction distributes. So these are, so to say, the 3 regimes. And I will tell you just in few words, how did we treat the problem and what came out of it. Now, really interesting, however, it does not get here. It gets interesting if you also lose nucleons out of the nucleus, right? So we have to check what's going on with nucleon loss. And there are two processes for that. One of them is neutron evaporation. Neutron evaporation is basically a statistical process. So you have a specific number of particle-hole pairs, and you have a specific total excitation energy. But all possible combinations of it, because you have several, you have several possibilities for a certain particle-hole pair number and total energy. And they're all statistically populated. And every now and then there's one neutron which is at the edge of the wall of the well and goes out. This is called neutron evaporation. So this will be the picture over here. The other picture is, so this happens actually only to neutrons because protons also have to pass the Coulomb barrier. So it's better for neutrons because neutrons are neutral and do not care about the Coulomb barrier. However, for the other mechanism where a photon comes and by mistake, if you want, so statistically, it can maybe not only elevate a particle from below the Fermi level up, but it can also be absorbed by this one particle, which is already excited, such that it's sufficient to get out. In this case, of course, the particle could also be a proton. So you can use protons or neutrons on one side, or you can use just neutrons via neutron evaporation. Actually, we have only considered neutron evaporation in our work because for nuclear emission, we needed some additional data, which is not easy to find, namely the density of continuum states. So there we've done just one estimate. So, okay, the idea would be, so if we are able to come with these coherent photons and have multi-photon excitation, we would probably be able to blow up the nucleus because we would continuously have particles coming out. And this is actually very cool and completely unknown because blowing up the nucleus, nobody has done, right? There's not much known about, for instance, nuclear emission or fission from highly excited states, right? States which are highly excited or states which are far away from eras, we just don't know. So in principle, if such a pulse would be available, one could try to have inspection of decay products versus pulse duration, intensity, or photon energy, and they would tell us something about the level densities or decay mechanisms or timescales inside highly excited nuclei. So let me show you what kind of calculations we have done. We have basically put together a master equation because we are describing basically only statistically the processing happening. And basically, we discuss only statistical features with level densities, so no discrete levels. So then we can basically write a probability for a specific nuclear species with a specific excitation energy, which we count as number of absorbed photons at a specific time. And this comes out of a master equation, which has here some terms. Now, it's for you probably ugly. I would just say the presence of these rows, the rows are the level densities. We'll just tell you we are talking about level densities and not about specific levels. And that whether we have W's or gamma or whatnot, it's good to know that this part has to do with photon absorption and stimulated emission. So it's the part of interacting with the laser. This is neutron evaporation. And one can also consider if one wants the induced fission. And now, if we consider now the quasi-adiabatic case, this equation is sufficient because we can assume that basically there is equilibration between particle-hole classes all the time. So we will not have to count what particle-hole classes we have, that we have one particle, one hole, or two particle, two holes, or three particle, three holes. So basically our matrix will be something which goes into the number of absorbed photons and blockwise for the species, because after losing one neutron, after neutron evaporation, you have another such block. But we will not keep track of particles and holes. And this will be for the quasi-adiabatic regime. So this was our first result. And right away, I will show you that things get more complicated if you really have to also keep track of the particle-hole states. Because then basically each entry of this matrix is itself a matrix. And this we've done as well. But just for you to see what kind of results you can get. So let's assume first we are just checking what's happening with the excitation without neutron evaporation. And we consider a generic nucleus with A100. And in this case, if you see here, excitation as a function of time for different strengths of the dipole width. So basically the excitation rate. Let's take maybe this 5 MeV middle result. What we see is that basically the occupation probability plotted here. So probability of occupation of a certain energy, so total energy state of energy E, is going up and is kind of getting saturated at some point. And the saturation has to do with the level densities, which are always having a maximum, and then they go down. And this maximum is at 550 MeV. And this is also the place where basically you cannot pass this point, right? Because then absorption will be dominated by stimulated emission. So basically the maximum of level densities is also the maximum of excitation, what we can get. And you see, basically you need to absorb 100 photons of 5 MeV. And now if you add to this neutron evaporation, actually you see that pretty quickly. See, this is the target nucleus, this is the first daughter, second daughter, third daughter, and this is kind of a dump. At some point we allowed the last daughter not to decay, that's it. So the interesting part happens here. Actually see that pretty quickly, far before saturation is reached, neutron evaporation will take you to the next isotope. And then here, again, neutron evaporation will take you to the next isotope, and so on. So basically it turns out that far before saturation comes in, neutron evaporation is very strong, which means that you go towards proton-rich isotopes. And actually a very similar result happens if we do the sudden approach. And there we need to keep track of the particle hole states and their couplings. So they are basically now metrics. We have each item that we had before, each element is actually a matrix itself, going in particle hole pairs numbers. And there, of course, it's also much more difficult to plot results because you don't have, right, for each particle hole pair, you could plot a plot as I've shown you before. And this is what you see here. These are, again, the total energy as a function of time. And you see a very similar behavior. So basically you see the onset of a saturation pretty quickly. And these are the numbers of particle hole pairs. Now for A100, you can have 48, up to 48 particle hole pairs, but we didn't plot them all. We plot them every third one because otherwise it's blown up. You have very, very many plots. And also here, basically, what you notice is that we are kind of staying on the curve of the level densities, which has a certain maximum at about 500 MeV. And these are the specific densities for specific particle hole classes. It turns out that those ones which have largest values are also the ones which populate where you see here a reasonable population. So see, basically starting from here, from the maybe green one, which is 25, right, is going up, then the gray one and the brown one or the red one and so on. These are the ones which are 25, 29, 33, and the ones which you see here have larger population. So it's kind of interesting and understandable. This is again a result where there is no neutron evaporation. It's difficult to see the neutron evaporation if you really look at the particle hole pairs. So this is why we can sum up to obtain a result for all particle hole pairs for different photoexcitation strengths. This is the case I've shown you before for the result without particle hole pair counting. And actually now if we take this result and we look for the neutron evaporation, we see that again we lose neutrons very quickly. So basically saturation will be never reached, but you will simply stay here somewhere. After very few septoseconds, neutrons will be lost. And this is actually qualitatively a very similar picture. So it's just in the sudden regime, you should have stronger photoexcitation, so things happen quicker, but neutron evaporation will depopulate pretty quickly your target nucleus. So it's the same also here, then one reaches proton-rich isotopes, or one produces proton-rich isotopes far from the value of stability. Okay, and with this, I noticed I spoke 1 hour, my goodness. I will come to my conclusions. I've been telling you 3 very different things. I hope it wasn't too much for the late evening. So I've been telling you about a nuclear clock based on a special transition in a special isotope called thorium-229, which could be a very good nuclear frequency standard and a different nuclear frequency standard. Then I told you about the new field of X-ray quantum optics, where we can design nanostructures which allow us to control single X-ray photons. And the goal there would be to try to design and establish such nano devices, if you want, which could control X-ray photons for quantum technologies, maybe also going beyond this single photon X-ray regime. And at the very end, I talked about science fiction, if you want, in the sense that if we would have coherent gamma ray photons, really at MeV energies, this would open a new parameter regime to understand nuclei which are highly excited. And this is basically a landscape that has not been available so far. So with this, I will thank all my former group members and present group members involved in the work I've shown you, and especially Shandin, and the funding agencies. And I do thank you for your attention.
Yes, thank you, Professor, for very nice and interesting talk. And actually, this talk is very new for the nuclear physics community, and with the strong laser and X-ray. And I think even in China, we have now quite a few strong power laser, and even for the gamma ray beam facility. So I think something could be done in such kind of facility. So now I think the session is open for questions. So there are any questions? So you can. Yes. Okay.
Yeah.
Please.
Hello. Yeah. Hello, Adriana. It's me, Jianxin. Nice to see you. Yeah. Nice to see you. Yeah. Okay. Very nice talk. Yeah. So I have a few questions on the topic of the MeV gamma ray photon interacting with the nuclei, because you claim you need the coherent MeV gamma ray, but I don't understand why we need the coherent gamma ray. For incoherent case, what's the difference?
Oh, this is very simple. For incoherent case, so basically in the picture that I've shown you, I'm trying to get this photoexcitation, right, to be of similar rate with the residual interaction. And the photoexcitation is basically determined by the dipole moment, if you want, right? It's E1 excitation, and we have the nuclear dipole moment. It turns out that, so to say, kind of single photon coming in will not be sufficient. What we do need is somehow to boost this photoexcitation rate. And the way that we considered it was, if I'm coming with n coherent photons, then basically the photoexcitation rate, the effective photoexcitation rate, is n times the single photon rate. Yeah.
Yeah. Okay.
So this is why basically in order to get a photoexcitation rate which is on the level of MeV as the residual interaction spreading width is, one would need to have, for instance, something like at least 1,000. So on the level of 1,000 coherent photons to have this factor n in front. So let's put it this way. If you're taking what we have right now, then you are in the perturbative regime. And what we were interested more in was this quasi-adiabatic or the sudden regimes, where photoexcitation comes in so quickly and so strong that there's not, the nucleus just has time to equilibrate, or maybe does not yet have time to equilibrate. Yeah. So that's the reason. It's basically to generate an effective dipole rate out of the dipole rate of a single nucleus, which is not sufficient.
But that will come to my second question: how to generate coherent gamma ray?
I can tell you what they say, right?
Yeah.
So what they say is that they would take a. So that's interesting for you because you're a plasma person.
Yes. Actually,
so I thought this is what you would ask. Yeah.
Yes.
In principle, what they say is that they would first shoot with an optical laser on a carbon foil to kick out a sheet of electrons. Yeah. And the idea would be to take the sheet of electrons and have a backscattering of another optical laser. But the sheet of electron, as it comes from this carbon layer, is maybe not yet perfect and not yet very dense because the electrons are still far away. So I understand that the plans would be right now. First, this one sheet that you have needs to be first basically colliding with another laser to obtain the mirror at the proper density and at the proper perfection, right? Because you need to have it pretty straight so that afterwards you can maintain via back reflection, back scattering, the coherence of an optical laser on this mirror. So these are the 3 steps. I mean, you first generate the electronic sheet first, then you prepare it in the proper density and proper quality, and then you backscatter. Whether it works, I mean, I've heard talks in both directions. I've heard people saying it's not going to work, and I've heard people saying it's going to work. What did work is up to, what was it? So up to, I think, XUV. So they did do such a thing and obtain coherent photons, but not MEV, of course, not MEV.
Exactly. Yeah, for MEV,
I know the paper.
It's really hard. Yeah, really hard for the generator coherent.
Yes. So
that's why we yes, we are aiming to generate MEV, but the hard. Okay, the last question. Okay, since the time. Okay, the last question. I mean, for the gamma photon interacting with the nuclei, do you think? I mean, of course, if we consider also the angular momentum of the gamma ray, would be very interesting because the angular momentum will change the excited states. Yes. So because now we also now we are interested in how to control the orbital angular momentum of the gamma ray, and we would like to calculate the interacting cross section of the So
you want twisted light in the gamma ray regime.
Yes.
But this also, has this been ever done, or it's just a plan? So I'm not aware.
It's no. We just calculate how to generate the orbital gamma ray photon in the laser plasma method. Yes. Yeah. So we recently just submit a paper to how to generate the orbital angular momentum with orbital angular momentum gamma ray. But now the next step, we want to calculate how to,
I mean, is it really gamma? Is it X-rays?
Yes, so it's gamma. Actually, we calculate it's gamma, but it's incoherent gamma, not coherent.
I will tell you what's so why I ask. So we were. If we go now up to 100 MeV total excitation energy, therefore definitely we discuss about level densities, right? If you're thinking now about absorbing a single photon at a few MeVs, then we are still maybe in the region starting from the ground state where you still have discrete levels. And often these discrete levels, say between 5 to 15 MeV, they are in the so-called giant dipole resonance regime. So this is a kind of a the way to model this excitation, the nucleus, is that you have a movement between the neutrons and the protons inside the nucleus, right? And this generates to you the giant dipole resonance. The giant dipole resonance is E1. So that's not what you need, because if you want to do twisted light, right, then rather for you, the cool stuff is at least M1, if not E2. I have the impression even with light, M1 is not so interesting, but E2 is kind of interesting. So one would need to find specific transitions where you still have these levels, which indeed, coupled to the ground state via their selection rules by E2. They are not so often. So the most typical situation is this giant dipole resonance, but that's maybe, I have never thought about this. What happens if you try to excite, whether it works, the GDR with twisted light? And this is interesting. I haven't thought about that, but I would say now first, the GDR is E1, so maybe it doesn't work. And then we would need to find specific transitions. They exist, but they're not so many.
So if
this sounds very cool. Is there any chance that you are on the archive of this paper, or you can drop me an email?
No. For the archive paper, we just submit a paper to how to generate the twist gamma photon. But
but I'm interested. I'm interested to see.
Okay.
So maybe you can you drop me a line by email?
Okay, no problem. Yeah, no problem. No problem.
Thank you.
Okay, then
Awesome.
maybe we can exchange the idea by email for the next steps. Okay, very nice, much.
Awesome.
Thanks a lot. Okay.
Thank you. It was great to see you again, to talk to you. Thank you.
Okay.
Okay, so maybe Bing Sing Du too.
I have a question.
Yeah.
Listen.
Thanks, Professor Ma. Yeah. Hello, Adriana. Yeah. Very nice talk. Thank you very much. And actually, I worked at Klaus Brown's group for pentatrap spectroscopy from 2017 to last year, actually. So I think I saw you several times in MPIK. I'm just wondering, so did you ever talking to Klaus or other pentatrap group to propose to do thorium isomeral state?
Many times. Yes.
Yeah. So what's the status and what's their response for that? Actually, I want to know.
Well, here, I mean, there are two directions. I mean, Klaus has been already for years laughing at us that by the time we are so good to measure the energy properly, he will also do it with the penning trap, right? To really measure the 8 electron volt, but as a mass. This is, of course, in my opinion, very, very challenging. I don't know whether he can do it at the moment. I think not. But definitely traps are one of the ideas of how to build the clock, right? So you would need, and this is decoupled of Klaus necessarily. So there are two approaches at the moment on the market in thinking of how to build a clock. One of them is to say we are going for this VUV transparent crystal doped with thorium. The advantage there is that you can put very many thorium nuclei in, right? So you can have quite large doping. The disadvantage is you are in a crystal. You have all kinds of broadenings. You need to have them under control. So I think one can get the clock on that. Maybe it will not be a clock which will beat all other clocks by, an order of magnitude because of the fact that you're in a crystal and you don't have such a controlled environment. The other approach is to put ions in a trap. But 1,000 ions in a trap, right? At most. And in both cases, what you need on top is to have the VUV laser, a narrowband VUV laser for the proper range. And I would have to say VUV, this 8.2 is particularly bad. I mean, there is this Chinese group which has a crystal which can act as a resonator for the laser. But that only goes up to specific frequency, and afterwards it drops because the photons are so strong they destroy the lattice of the resonator. And this I know there's just one Chinese group which can, I think in Beijing, can grow these crystals. This is very special to grow them and to cut them. But it's very difficult because again it does not work for the full UV range. And then depending exactly where the transition is, one could have that approach or not. So right now, actually, the people I know work on frequency combs. Trying to build.
I know, but the thing is, I think Klaus once proposed to really measure the state, really measure the isomer state. So in a penny trap to determine the energy in high precision. So all just to scan by the laser. So in a penny trap.
But you need a laser. Again, so the laser is not available at the moment on the market.
Yeah, that's the thing.
So this needs to be built.
That's the thing. Okay, I see. Okay. Yeah, thanks.
Thank you.
Okay. So, any more questions?
Can you hear me?
Oh, yes. Please.
Professor, I'm a PhD in Fudan University. So I have a EA question. Is what do you think is by far the most effective machine to exit 229 pH energy levels?
Wait a second. So this is about thorium-229. Could you repeat the question a bit louder? I have difficulties to hear you.
What do you think the most effective machine to exit 229 pH?
Measure the energy.
229 is
Do you ask me what's the most efficient way to measure the energy?
yes, width is most effective. Must be, can you understand?
So, okay. So,
Yeah,
not-
so, okay, he type
you did,
in the chat.
which is great because this will help. Wait a second, where's the chat? What do you think most effect makes to excite the energy level? Yeah, okay. So thanks a lot for typing it. That's great. I also put my loudspeakers on maximum. So I'm not so sure it's so important what's most effective. I think we all do this for the right. I mean, the whole interest about thorium is about the nuclear clock. And for the nuclear clock, we need to have a narrow band UV laser, which can resonantly drive this transition. And no matter what application you want, right, everything we think of has to do with this nuclear clock. If we want, for instance, to test Lorentz invariance, if we want to test Einstein's equivalence principle, if we want to check variation of fundamental constants, we still need to be able to drive that transition with a narrowband laser on resonance, right? So this means, I mean, no matter what's right now the most efficient mechanism to do it, as an outlook, we need to be able to have that laser. So this is paramount, and there are several groups in the world which are now working to have a VUV laser in that region. Otherwise, right now, what have they done so far? Well, they've done a number of things. One of them was that uranium-233 decays via alpha into thorium-229, and 2% does not go to the ground state, but ends up in the isomeric state. So this is actually the one population mechanism which has been used so far in several experiments. No, in several experiments, this is what they've used. But this is, of course, very bad because it's completely uncontrolled, right? You have a uranium target, and this disintegrates radioactively by itself with absolutely no control and no time trigger, right? So it's just happening. So this has been used many times. The Japanese group has been using at Spring 8 the 29 kV transition. So they pumped from the ground state to the upper state, right? This is I have the scheme. So here, yeah. So there is an experiment performed, published in the same Nature issue in 2019, which goes up here, right? So you populate 29 kV, and there's a good branching ratio to go to the isomeric state. This is another way, which is a bit more controlled into the respect that at least you populate the upper state controlledly, right? And then you, however, need to see that it decays by itself. But it's still not the alpha decay, right? So there's a little bit of more control. But eventually, we do need the laser. So, yeah. Does this answer your question?
Okay, thank you.
Okay, thank you. So now a question goes to the Guoqiang Zhang.
Hi, Professor Pálføry. Nice to meet you. I'm Guoqiang from Shanghai Advanced Institute, Research Institute. We have some free electron laser in the near future. So if you are interested, maybe you can come to do some experiment here. But here I have some question on one question on the last topic you are talking, the very high excitation state in nuclear. Is it possible to populate such a kind of state with current excitation from very heavy ion peripheral collision to populate this kind of state. Maybe I'm missing something. You say you need some coherent MeV gamma photon to populate this some spatial state. Maybe I can get the point you are talking.
Okay, let me see. I will go here. Okay, so about Coolix, let me think.
Very peripheral collision, but not fusion. Maybe is it possible to populate this kind of very high energy excitation state with very low angular momentum?
Yes, I understand your point. So you say basically,
But
so far,
it may be some virtual Coulomb excitation. It's not real one.
Virtual Coulomb excitation. This is an interesting idea. I am not so familiar with virtual Coulomb excitation. I think the regular Coolix is used. I'm not aware that they ever went so high, but like several hundred MeV excitation energy, but maybe nowadays it's possible. This maybe the nuclear experimental physics experts might know. So our idea was that you typically want to. So see, what's our interest? Our interest is very statistical. One wants to have these multiple excitations. One wants to have many excited nucleons. And you're just thinking, how did people do this before? Very often it was so that it was through the formation of the compound nucleus, right? So basically, I'm sending an alpha particle, for instance, on a nucleus, and it stacks, right? So it's this kind of fusion. Or a proton or a neutron, and then they stick together. Then there is one excited particle, which comes now with basically a lot of energy, and that energy is distributed over several particle Hall pairs. And this is the regular way to excite the compound nucleus. So I think our thinking was more coming from this picture of compound nucleus and saying, now, if we have these gammas coming one after the other, each of them bringing just 5 MeV, but you have several coming in at short times, then you excite one particle Hall pair, second, third, fourth, fifth, right? And then you have a compound nucleus which has been reached by a completely different mechanism, and then it has little angular momentum. So this was our idea, but maybe what you say is try to bring in, for instance, a couple of times a Coolix with a bit more excitation energy, right? Say if you manage to do a Coolix with 10 MeV or 20 MeV, I would say that maybe it's, so if we would have these coherent photons and they would work properly, probably you could go at higher photoexcitation energies. However, as long as you do not have them, probably one should try to look at Coolix alternatives. So the idea is not bad. But we have not looked yet into that. But our interest is definitely the compound nucleus, right? So this is the idea of having many excitations and having this interaction via this residual interaction, right, between several particle Hall pairs, and this interplay of how energy is redistributed. This is for us interesting, or was interesting in the project. The compound nucleus part.
Okay. Thank you.
Thank you.
So like in the relative statistic heavy ion collision at ultra briefly collision, so there are very strong electromagnetic field. So in this case, yes, maybe, yeah, but it's at a very high energy heavy ion collision. Yes. But my question, to Professor Pálføry. So, if we have a very strong magnetic field, so what kind of things can do for such kind of physics of your institute?
Very strong magnetic field.
Yeah.
I'm not sure exactly to which part you are interested in. So I think typically it's so, isn't it so, that because we have the electrons, the magnetic field which are experienced in the nucleus are anyway pretty strong because of the electronic motion. So I think externally it's very difficult to generate very strong magnetic fields which would affect the nucleus.
Yes.
So it's more, I can tell you, for instance, but it's only partially related. So right, external magnetic fields, we typically can work on the levels of few Tesla reasonably well, and not so easy for more. But it turns out that in our iron, I mean, there are certain crystals in which the electronic spins, which can be very easily oriented with some very weak magnetic field, generate at the nucleus a 33 Tesla magnetic field. And that's actually a magnetic field which is very strong, but it's generated by the electrons. So I think typically our handles, or so to say, our tools are rather going via the electronic spins, right? And if we can control the electronic spins will at the nucleus generate very strong magnetic fields. This is actually interesting, and in the X-ray control part, so it's basically where are we here, right? So this taming X-rays, X-ray quantum optics schemes, we do have this often that we are wanting to have the 33 Tesla magnetic field generated by the electronic spins. For the other two processes, for the other two projects, I cannot say. So for thorium, it's also so that there will be strong hyperfine splitting in the crystals, for instance. But otherwise, I'm not aware of how much this would mean.
Mm-hmm.
And now that you just mentioned about the heavy ion collisions at CERN, actually, this reminds me that once somebody from Heidelberg who works with Atlas was also asking us about such a, if it's possible to consider this kind of photon excitation in the CERN collisions, lead head-on collisions. So actually this idea touched us once a few years back, but we did not start anything in this direction. So maybe it's a good time to think again about it. Yeah, interesting.
Yeah. So since in the at RIC, Brookhaven National Laboratory, or even at LHC, so the magnetic field could be reached more than 10, 14 Tesla. So it's a very, very strong magnetic field. So maybe, yeah, it's interesting to do some prediction or something. Yeah. Yes. Okay. Okay. So, any questions? Oh, okay. I see. Zhao Jie.
Yeah. So thanks for the nice talk. I have a very naive question. So on your photonuclear interaction, the particle and Hall pair production, what's the difference between this and the what you're talking about, the ground dipole resonance?
Could you repeat the question? So it's pair production?
Yeah. I mean the difference between the particle Hall pair production and the ground resonance, ground dipole resonance.
What type of resonance?
Ground dipole resonance, GDR.
GDR. Oh yeah. Okay, sorry. I'm sorry. It's difficult. Okay. If I don't see you, it's difficult. Okay, so let's put it this way. So with the GDR, it's so that you come and put in energy, right? You come with a photon which is 10 MeV, and then it turns out that the eigenvalues, so the eigenvectors, so the eigenstates of the system are actually not are kind of distributed via its very similar mechanism as the residual interaction, and then basically you have this spread of the GDR over several very, very large dipole width. So to a certain extent, it is very similar to what you say here. It's here it's the same, right? You have energy coming in and energy is distributed by the residual interaction. It's just the type of interaction that we consider here is these collisions, basically. The nuclear collisions are a bit different than the type which appears in the GDR, but the mechanism, if you want, it's similar. So indeed it is, so you first excite the particle hold pair and then the energy is redistributed in our case. And in the GDR, very similar mechanism happens. So it's basically related. It's just the nature of the interaction, so to say, which is the residual interaction is different. So the type of the term in the Hamiltonian is different, but the mechanism is in the idea itself that the energy is redistributed over many states is the same.
Mm-hmm. Yes.
I can send you, actually, we have quite a exhaustive discussion about this in our last paper. So if I may, I can send it to you if I get an email, but this one. So in this PRC paper from last year, actually we had in an introduction, we had a discussion with the referee about this. So it's quite clearly explained.
Okay, thanks. I will see the papers. Thank you.
Yep.
Okay.
Or send me an email. I can send it to you.
Yes. Okay, maybe Zhaoji, yeah, you can contact Professor Pálføry for this topic.
Okay. Actually, as Professor Ma already introduced, actually we are doing heavy-ion collisions. Actually, in heavy-ion collisions we have some kind of photonuclear interactions, like with very strong magnetic field, like 10 to power of 14 Tesla. Yeah.
Mm-hmm.
And what do you do with them? So what would be the application? So what happens?
So because you have magnetic field, then there are spin, something like spin. You know, photon has spin 1, so there may be some couplings between this photon spin and the strong magnetic field, or some other kind of sense. Actually we do not know right now, but yeah.
But that's actually very interesting. So this kind of brings me back to the discussion. But again, it's 3 or 4 years ago we had the discussion about with somebody in Heidelberg about something similar, and we said, yeah, okay, we'll think about it, and nothing came out. So maybe one should talk, because I would also be interested to know what happens, right? So how can we describe this, and what could be expected? So it's good that I gave this talk. I have not spoken about this part for a while, although we have these new results from last year, but somehow I think the last talk I gave was 3 years ago. So I didn't get so much feedback, so to say, on the topic. It's very good to talk about it again. Thank you.
Okay, thank you.
Okay, so maybe, yeah, we have already a very long time for this seminar, and thank Professor Pálføry again for very nice talk and interesting discussion, and hope to, really like invite to visit Shanghai and China for near future, and
when it will be possible.
Yeah, I think it's possible. Now China is almost the policy for the COVID is really just changed very recently. I think next year will become regular as Western countries. Yes.
Let's hope so. It would be nice. So I would be delighted. So and I will definitely be. I'm definitely interested to come once it's easy to travel, right? So, but thanks a lot. Yes. Also from me, thank you for staying with me so late and also so long. It has been a long talk and a long discussion, so I appreciate.
Yeah, we are really enjoying your talk. Really,
late talks. I enjoy late talks.
Yes.
Yeah.
Okay.
Nice.
So
thank you so much
bye-bye.
For your attention.
Thank you a lot.
Thank you.
Yeah.
Thank you.
Okay, bye-bye.
Bye.
Bye-bye.
Thank you. Bye.
Bye, Captain. Bye.
Bye-bye.